All right, as you can see, we're doing Unit 6, Part B, number 1A through D. It's set, okay, so they have told us that f of x is cosine of the square root of x, and we have to approximate the definite integral using a midpoint Riemann sum with the subintervals given to us. Show the work leads to your answer. Okay, so Riemann sum again. I think this is the second question regarding this. It's a little surprising how many Riemann sums questions we had. Kind of like the intermediate value theorem. I mean, I think we had 3, 4 of those, which is a little bit overkill if you ask me. Okay, so we're doing midpoint. So midpoint, we don't do that very often either. All right, so let's say we've got our function. It's going to start, well, it goes from 1 to 3. So I'll say this is 1. And then it goes from 1 to 1.6. So we'll call that 1.6. And 1.6 to 2. There's my 2. And 2 to 3. 3. Okay, so I will just call this, well, here's my function. There. Okay, so if we want to approximate my function using the midpoint, Riemann sum, so you're going to end up with 3 rectangles. We're going to have a rectangle right here, there's one, and there's one. And then the height of the rectangle is determined by the midpoint of the interval. Okay, so your first so the area is approximated using midpoint theorem. First base is 0.6. Your first height is, well, it's 1.3 is right in the middle. So it is, this ordered pair right here is 1.3 comma f of 1.3. This ordered pair here is 1.8 comma f of 1.8. And then the last ordered pair is 2.5 comma f of 2.5. All right, so my first rectangle is base times height. So f of 1.3 is my height, so it's the cosine of the square root of 1.3. My second rectangle base is 0.4. My height is f of 1.8, so the cosine of the square root of 1.8. And then our last rectangle base is 1 times our height, which is this cosine of the square root of 2.5. Okay, so that's part A. That's an approximation using midpoint Riemann sum. All right, part B. Approximate the definite integral using a trapezoidal sum with the subintervals. Okay, so luckily they give us the same subintervals. Show the work that leads to your answer. Okay, approximate using trapezoidal sum. All right, so I'll use the same drawing. Here's my first trapezoid. There's my second trapezoid. And there's my third trapezoid. Okay, so remember, area of a trapezoid is 1/2 base 1 plus base 2 times the height. So our area is approximately the area of the 3 trapezoids. The first trapezoid here is 1/2. Base 1 is this, which is f of 1, or the cosine of the square root of 1, plus my second height is the cosine of the square root of 1.6. And then times our height of our trapezoid is 0.6. Plus 1/2 this base 1 plus base 2 times 0.4, and then 1/2 base 1 plus base 2 times our height, which is 1. Add them up and get your answer. All right, part C. Okay, so they give us the first derivative. I don't know that we'll even use it. Our second derivative is given to us. We could have found it. But they actually do the derivative for us, which saves a little bit of time here. And I'm not going to do the second derivative to see if they got the same answer. Okay, so there's our second derivative. Would a trapezoidal sum approximation from 1 to 3 overestimate or underestimate the value given from 1 to 3, given a reason for your answer? Okay, so if it's all about the concavity, it's not whether the function is increasing or decreasing, it's whether the function is concave up or down. So luckily in my interval here, 1 to 3, my little curve that isn't cosine the square root of x, I just made it up, but it actually has concave up and it has concave down. If you notice, when it's concave up, a trapezoid is an overestimate because it goes above the curve, and when it's concave down, it is an underestimate. So we just need to know what the concavity is in the interval from 1 to 3. So we need to know how the second derivative looks from 1 to 3. So grab our calculator. We type in our second derivative. I went from 1 to 3. I did pretty small y mins and maxes just to have a look at it. And if you graph, you can see that the curve, pretty exciting. It's a little line or a little curve there, but it is above the x-axis. That's all we're looking for. So in that interval, we know that f double prime of x is positive for x between 1 and 3. Therefore, it's concave up. And since it's concave up, therefore it is an overestimate. The trapezoid is actually more area than the actual area underneath the curve. All right, that's A, B, and C. D, time for another sheet of paper. Write the integral 1 to 3 of f of x dx as a limit of a right Riemann sum with n subintervals of equal length. All right, so again, we haven't done a whole lot of this, if any. So we have to write this as a limit, and it's a right Riemann sum. Okay, so basically just to, well, we know this is from 1 to 3, the cosine of the square root of x dx. Based on that, we know a couple things. We know a is b, we know b is 3, and your dx is on the, well, that's kind of our delta x. Dx and delta x are kind of the same thing. This is an approximation of dx. Okay. We also know that b minus a over n is our change in x. So we always called it h. So if you want to figure out how much we're going up by, you do b minus a and divide by how many subintervals, and that's what you're going up by. So your delta x. So if we're going to add up a whole bunch of intervals or rectangles, so I'll just call this, there's a, which is 1. If I wanted to add up this, and then another one, and then another one, all the way up to 3, we would want to, well, each of these rectangles are delta x, that's our bases, and our heights are determined by whatever the y value is. Now remember, we're doing the right Riemann sum, so our first rectangle is determined by the height of your first, let's see, not f of a, but f of delta x, or a plus delta x. So we have our first rectangle is our height, which is f of a plus delta x. times our base. I'm doing it backwards just because normally I do base times height, but we're going to do height times base here because we'll put the delta x at the end like it normally is in an integral. Okay, so there's my first rectangle. Plus my second rectangle. Well, the height is now f of a plus 2 delta x's times our delta x. So we go 2 delta x's to the right of a to find what our x value is and find f of that. So you can see where this is going, 3 delta x and so on. So if we add up all of them, we get our answer. And if we have an infinite amount of them, we have a limit to approximate our integral. Okay. So if we have integral from 1 to 3 of the cosine of square root of x dx, it's approximately the limit as n goes to infinity. We'll say k equals 1 to infinity. So f of our a is the same a we said is up here, 1 plus, and you can see that our first k is 1 and then 2 and 3. So we can say k times delta x times delta x. If we add up all of those, we have our approximation of our integral. Okay. So this is our a. It's always a right there. And this is always your delta x, and it's always k times delta x right here. So this is kind of the general form of a Riemann sum. Okay, so now just to fine tune it for this problem, our f function is the cosine, the square root of 1 plus k, and then we can figure out what our delta x is because it's 3 minus 1 over n. So it's 2 over n. So k times 2 over n, and then delta x on the outside again is 2 over n. All right, so hopefully this makes sense. Yeah, and I did it in 13 minutes. I was worried if it would go over to 15 or not. Have a good day. See ya.